This is the handout that in addition, this is the lab for next week. This is
Oh, okay. Do I need a copy of that?
yeah, it's in Brightspace.
Okay.
I wanted to show it to you so you'd recognize it when you see it.
So this time I print that out and bring it with me.
Yeah. Plus, there should be another document along with it. It's an explanatory document about calculations.
Okay, okay, sounds good. So next time come to lab with both of those documents.
Right.
Okay, perfect.
Yeah. And since this is a formal lab, your notebooks need to be set up correctly for.
Okay. Numbered and everything. Okay. Got
Yeah.
it.
Because theoretically, you go into the lab and you perform the lab based working from your lab notebook. A hard copy is nowhere in sight. Okay. All right. Now let's get going before I eat up too much of our time. Review for the second exam. And this copy of the review, for some reason, I restarted numbering when we got to chapter 4 review questions. So that's why I put chapter 3 up there. And then when we get chapter 4, I'll start numbering again. I've highlighted some of them that I want to be sure and get to, but I want to not miss out on any questions that you have. If you run through these review questions and found any that were unsolvable, we need to do those first. Or if as we proceed, if you think of one that's bothering you, then let me know and we'll detour. Okay. That being the case, let's do number 1. Naturally occurring copper exists in 2 isotopes, copper 63 and copper 65. The atomic mass of copper is 63 of the atomic mass of copper, and this is the weighted average value for copper, is 63.55. What's the approximate natural abundance of copper 63? All right, we're not given exact values for the masses of 63 or 65. So we have to work from the mass numbers, right? Instead of, okay, otherwise you would be given a decimal fraction that was close to 63 and one that was close to 65, and you'd work from those. But in this case, we have to work from the others. Now, the weighted average is you take the I call it the decimal percent, the decimal equivalent of percent, and multiply it by 63 for the first one, and then 65 for the second one. So to get the weight of each one, we need 63 times whatever its abundance is. That's our unknown. And once we find that, then we got the answer to our question, the natural abundance of 63. So if these are the only 2 isotopes, what would the natural abundance of 65 be on a decimal basis? If it were percent, it'd be like 100% minus whatever this percent is. But we're using decimal equivalents, so it'd be 1 minus that number. Okay? So once we get that value out here, we would add them together. And since we don't have anything for x, we would simply add these 2 together anyway. So it would be 63x plus, I'm going to go ahead and multiply this out. 65 minus 65x. Okay. Did I lose anybody? 65 times 1, 65 times x, the minus number. And that would add the relative abundance together. And if we had values for x, we'd get an actual number there. But since we don't, well, actually, we do have a number there, don't we? 63.55. That's what the weighted average is. Okay. All right. So we just need to solve for X. And if I do, let's see, put the X's together, you get what? Minus 2X plus 65 equals 63.55. And then, I guess we can do it this way, 2X. And then minus 65 from that side would be what? or 1.45. Is that right? Minus 1.45. Because when this one comes over, it's a minus. Right? That one comes over to this side, it's minus. That means the difference is a minus value. And let's see if that adds up. Yep. Okay. So the minuses go away. And X equals 1.45 divided by 2. And if I do my math correctly, well, I might as well do it. Wouldn't hurt me to calculate again. 1.45 divided by 2. And that's 0.725. 0.725. And on a percentage basis, just times 100, right? So that'd be 72.5%. Relative abundance of this isotope. Now, notice that there are no answers in there that's 72.5. So what you do on a multiple choice is pick the best answer. And the best one in this case is, and the magic word there is approximately 70%. Okay? I just threw some algebra at you, that's all. Everybody's finished algebra or in it now, right? Okay. And that's about as bad as the algebra gets in this. It's just solving equations for one unknown. We throw fractions at you too. Okay, how about number 3? The average mass of carbon atom is 12.011. Right, that's the weighted average. Right? Assuming you were able to pick only one carbon unit, the chances that you would randomly get one with a mass of 12.011 is what? 0%. It's a weighted average. It doesn't represent any one atom at all. That's just a reality check. Okay, number 4. What's the mass of 4 atoms of copper in grams? So we're starting off 4 atoms of copper. And we want to know the weight in grams. This is a dimensional analysis problem. We're using conversion factors. So what do we know relative to atoms that will give us a mass? The atomic weight. Yeah, the atomic weight. So if we're going to work backwards, we need grams and moles, right? That's how atomic weight is expressed, grams per mole. And if we write it that way, then grams is on top here, and something over here has to cancel moles. Right? It has to be opposite because we can't have moles over there. And we don't have any moles here. So what we have is, what's the ratio or the conversion factor that would give us moles from this value? Atoms on the bottom, right? Do we know a ratio that'll do that?
Is it the 6.0?
Avogadro's number. Yep. 6.022 times 10 to the 23rd. There we go. Now we check ourselves. Numerator, denominator, numerator, denominator, and we're left with grams. Well, what we need is the molar mass of copper, which is, go to your periodic table because it's not given in the problem. So you got to look it up. 6355. Okay. So In your calculator, 4 times that, and that answer divided by this gives you grams. And if I do my calculations correctly, it should be 4.22 times 10 to the minus 22 grams. 3 significant figures. Now, we're actually not limited because conversion factor, those are exact numbers. They don't limit us. Plus, this is a counting number. It's an exact number too. So we can have as many decimals as we want out here. I just call it quits at 2. All right. Number 6. You have a sample of zinc and a sample of aluminum. You have an equal number of atoms of each. Right? Doesn't matter how many, they're equal numbers. Which of the following statements concerning the masses of the samples true? So if we have an equal number, zinc and aluminum, so we have so many like X moles of zinc, and then well, that's X moles of aluminum, same amount. We will say which one of these expressions would be accurate in terms of their relative masses. So A says the mass of zinc sample is more than twice as great as the mass of aluminum sample. Well, if we're going to have to make a numerical comparison, we need to know what those values are. So let's just say, all right, let's just say it's 1 mole, right? If they're equal, it doesn't matter. We get to pick. So 1 mole of zinc is 6538. 6538 grams per mole. And aluminum is 2698. 26.98 grams. Right? If we have 1 mole of each, that means we're comparing 65 grams to 26 grams. So if A is correct, then the mass of zinc should be twice as great as this mass. All right, we can estimate. If this is roughly 27, twice that would be 54, wouldn't it? Okay, so yeah, it is more than twice that, easily. So A is a good answer. A is a good answer. Now, do we have any squirrely ones in there? The masses of each are equal? No, we don't have any ones like 2 of the above or none of them are true and all that. So once you find the right answer, you can move on. And A is the best answer out of this one. All right. We incorporate a little test-taking technique in our reviews too. 7. Sample of ammonia has a mass of 43.5 grams. 5 grams of ammonia. That's ammonia. If you don't remember what ammonia, the formula for ammonia is, just ask me. I'll tell you. So the question is, how many molecules are in this sample? Well, our answer is in molecules, right? So we need conversion. I think I said at the very beginning that a lot of chemistry problems are solved by conversion factors. Right? Dimensional analysis will solve a lot of chemistry. This is one of those cases. So we've got to go from mass to numbers before we can find out how many molecules. And that's your best way to do it, is grams and moles. So what we need is a molar mass for ammonia, right? So 14.01, rounded off to 2 decimal places, is how many grams of 1 mole of nitrogen. And then 3 hydrogens would be 3.03, right? So that's 1704. Okay, that takes care of grams. Now we can convert to molecules with our buddy, Avogadro. Right? That's the thinking part. The rest is number crunching. Right? And if we crunch the numbers correctly, we should end up with 1.54 to the 24. 54. Yeah. Molecule. Okay. Number 8 coming up. Let's see, how many moles of hydrogen sulfide are contained in 49.7 gram sample of a gas? All right, I'll just set this one up and we'll move on because I don't want to use up a whole lot of time. You need to be able to write the formula for hydrogen sulfide to answer this question. If you have 49.7 grams and you're going to moles, you have to know the molar mass. You can't get it unless you know the formula for hydrogen sulfide. Hydrogen and sulfur together. Sulfur is a chalcogen, which means we give it a -2 charge, and hydrogen's +1. Well, actually, it's not charged, but it's our old good old friend oxidation state. So then we need to calculate the molar mass. Right, that's for the hydrogens, and the sulfur is 3207. So that's 904, 34.09 grams, moles. And this is 34.09. And if we divide that into it, it's going to be like 1 point something. 1.46 moles. Okay. And let's see, scroll down, we'll skip a few, come to 10. For which of the compounds does 0.256 mole weigh 12.8 grams? All right, 0.256 moles weighs 12.8 grams. So if it were me, I would just calculate the molar mass based on those values and then calculate the molar masses for each of the others and compare them. Okay, so first thing we want to do is 12.8 grams per 256, 0.256 moles. This will give us molar mass of one of those compounds, maybe. Since E says none of these, it could be none of them. 12.8 divided by 0.256 is 50 grams per mole. Okay, now I go back to Henry Ford, set up my assembly line. That's none. And I put in the compounds, C2H4, O, CO2, CH3 methyl chloride, and C2H6 ethane. All right, so let's calculate the molar masses of each one of these. We may only have to estimate, just to get close. So this is 16, this is 4.04, and 12.01 times 2 is 2402. 24.02. So 24 would be 28 and 44, about 44. Okay. All right, so that's nowhere near. I mean, if it gets really close, then we'll go in and calculate the exact value. But that's so far away, it doesn't matter. 12.01 for carbon and 32 for the oxygens, right? 16 times 2. So that would be 44. That's not it. How about this one? 12.01 and 3.03 and 45 for the chlorine. So that's 15. That's pretty close. Let's calculate that one exactly. $50.49. That's a good candidate. And this one is 24.02 because of 12.01 times 2, 6.06. So that's about 30, actually 30.08. That's not it. And so if it says for which compound does that much weigh that much? Okay, what we have to do is round. I would say this is the best candidate right here. Now, if you said none and you're sitting in your seats and I mark it wrong, you can come to me and show me your work. Say, look there, it's not exactly that one. So I'll give you credit for it. That proves to me that you're thinking. 11. Calculate the molar mass of barium sulfite. All right. Sulfite. There's nothing up here that would correspond with sulfite. That's got to be a polyatomic. So you look up your polyatomic in the chart. We know barium is this, and sulfite happens to be that, with a -2 and a +2. Right? Yeah, barium's an alkaline earth, so it's a +2. That's it, BaSO3. So now we can calculate the molar mass. Barium is 137.33. Sulfur is 3207. And 3 times 16 is what? For oxygen? 48, right? Let's see here. That's 4. This is 17. And that's 11, 217.40 grams per mole. Yeah, E. Okay. If I blow through a problem too fast, just holler at me, stop me. You know, if something doesn't click. 13. What's the mass of 6.761? 6.761 moles of what? Sodium hydroxide. Right? Good old lye, drain cleaner. Sodium hydroxide, which is a polyatomic. That has a -1 charge. That's an alkaline metal with a +1 charge. So that's all you need. Well, let's see. Sodium is 2300. Right? Oxygen is 16 and hydrogen is 1.01. Let's see. Yeah. 40.01. So if we're going to convert this to mass, we need moles on the bottom, grams on the top. That's 40.01. 40.01 times 6 would be what? 270 in the neighborhood. Yeah, 270.4. Okay. When my mind's working good, I like to do it in my head, just to keep things lubricated. Let's see. 15. One molecule of a compound weighs 2.93 times 10 to the minus 22. 2.93 times 10 to the minus 22 grams per molecule. I think that's what that says. One molecule weighs that. The molar mass of the compound is what? Well, we have a ratio of mass to numbers. Trouble is, that's not moles. Not yet. So in order to report the molar mass, we need grams per mole. So that one has to be changed to moles. Moles needs to be on the bottom of the outcome. So we need to cancel molecule, right, for one mole, and that's Avogadro again. Right? So if we multiply those two together, let's see. This would be about 60 times 3, 180. Thereabouts. 176 grams per mole. You can do it in your calculator if you don't feel comfortable working them in your head. Or you can bring your slide rule to class.
Pretty much.
Your slide rule. You ever seen a slide rule before? No, that's what we use before calculators. Well, they vary. Some of them are this long and some of them are this long. Engineering slide rules are like that. They're massive. So when I lived in Atlanta, occasionally I'd have to drive by Georgia Tech, and it was a status symbol. You know, who's got the biggest slide rule hanging from their belt? Okay, enough of that mess. Okay, we did that one already. 17 coming up. Okay. The slide rule is essentially based on logarithms. The scale is logarithmic. So if you add logarithms, it's kind of like multiplying the anti-log. A compound is composed of element X and hydrogen. Okay, so far we've given that. Let's see what else it tells us. Analysis shows the compound to be 80% X by mass. So it's 80% of X mass. Okay. With 3 times as many hydrogen atoms as X atoms per molecule. 3 times as many hydrogens as X. So the ratio is 3 to 1. Which element is element X? Okay. Let's see. I don't always follow the worked problems with these. Sometimes it gets me in trouble too. So if we're saying it's 80% X, suppose we have 100 grams. Yeah, let's assume 100 grams of the sample. That means X would be 80 grams, right? 80 grams of X, and what's left over is hydrogen. 20 grams of hydrogen. There you go. I think I'm starting correctly. Okay. We want to find out what element X is. So, and this is that many. No, that's the wrong way. I'm going about that the wrong way. Sorry. This is 1 mole if we have 1 mole of this compound, that means we have 3.03 grams of hydrogen. Okay. And if this is 80%, then this must be 20%. Correct? All right. So this is grams of hydrogen. And let's see, is 20%. So that would be 0. Or we could do it this way. Out of 100 grams of the compound, 20 grams is hydrogen. Okay, so that gets rid of this. And that tells us the mass of the compound, doesn't it? Yeah, that tells us the mass of the compound. So I'm just going to take 3.03 and divide by 0.2. So that's 15.15 grams per compound. Okay. If there's 1 mole of the compound. So if that's 20%, what's 80%? What's 80% of that? Right? That's 12.12 grams. And we were saying 1 mole, weren't we? We were talking about 1 mole. So that's 12 grams per mole. That's carbon. Right? Now, don't ask me what that compound is because I've never seen CH3. Not out sitting off by itself. CH4, yes. CH3 is always attached to something. Methyl groups. Okay. So somebody who made up this problem just pulled it out of thin air and didn't know what they were talking about. It was probably a graduate student trying to make a few extra bucks on the side. Now, I may have worked it differently in the worked problems. I probably did. But if anything, that illustrates that there's more than one way to work a problem. Which compound contains the highest percent of by mass of hydrogen? Okay. Now we're talking Henry Ford in spades. Each compound, HCl, water, H2SO4, H2S, and HF. Oops, I don't know why I wrote that. Okay, we're looking for percent by mass of hydrogen. So in order to do that, we need the molar masses of each one. Okay. Chlorine is 3545. And 1.01 for hydrogen is 3646. I'll put the numerator in there in a minute. We know this one, we've calculated it 100 times. And sulfuric acid, hydrogen is 2.02, sulfur is 3207. And oxygen 4 times 16 is
4 times 16.
64. Yeah. 9809. 98.09. H2S, there's sulfur again, 3207. 32.07. And then 2 hydrogens, 2.02 is 3409. And HF, fluorine's 19. So that's 20.01. 19 plus 1.01. Now we can put the hydrogens. Let's see, it was hydrogen, wasn't it? Yeah, mass of hydrogen. That's only one of them. That's 2 of them. 2 again, 2 again, and 1. These are each times 100. If we're talking percent. Okay, there's my assembly line. Now all I have to do is calculate. 3646, and that's 27.7. This is percent hydrogen. So 2.02 divided by 18.02 is 11 point, let's see, 11.2%. Did I do that one right? Let me try that again. I think I messed up. Oh, I know. Decimal's in the wrong place, isn't it? I bet it's that. Let me check it just to be sure. Yeah, 2.77%. Let's see, 2.02 divided by 98.09. That's 2.06%, or yeah, 2.06%. That's good. And then 2.02, 34.09 is 5.9, 5.93%. And then 1.01 divided by 20.01 is 5.5%. Okay. So the highest percent hydrogen is water. And that's the only way to do it. You just have to set up your assembly line. You're doing the same calculation every time, you just changing the values. I like to do it that way because it keeps me from making bad errors. If I try to do each calculation separately and then go down and start all over again, if I set it up like this, then I can catch my mistakes for the whole problem first. Well, except for reading my calculator wrong. All right, 19. A substance contains 35 grams of nitrogen, 5.05 grams of hydrogen, 60 grams of oxygen. How many grams of hydrogen are there in a 153 gram sample of this substance? All right, let's put what we know up there. 35 grams of nitrogen. Okay. And 5.05 grams of hydrogen. And 60 grams of oxygen. All right. That's the mass ratio of each one of these elements, right? And the law of definite proportions that was given to us by Proust says that it doesn't matter how much of this substance you have, that ratio is going to be constant. Okay, so if we want to find out how much hydrogen, let's see, yeah, grams of hydrogen there are in a sample of 153 grams, right? Let's find out what that total is, right? 10, 1 and 100.05, right?
Oh.
Is that right?
Mhm.
That's the total. Okay. So we're essentially saying that hydrogen is 5%. So if we multiply 153 times 0.05, we ought to get close enough to pick the right answer. 7.65. A is the closest one. Yeah. If we actually calculated that out, 7.72 grams would be the actual amount. And all you have to do is say, all right, here's the ratio, 5.05 over 100.05 times 153. Because that's the ratio times the actual amount given. And it should be 7.72 grams of hydrogen. That's just an illustration of the law of definite proportions. All right, moving on. 22. Each molecule of testosterone contains 19 atoms of carbon plus other atoms. The mass percent of carbon in testosterone is 79.12%. What's the molar mass of testosterone? All right. The fact that it's testosterone is irrelevant, except for the actual amount, ratios. But we could make this problem up about any molecule. 19 atoms of carbon. Each molecule has 19 atoms of carbon. And then it has something else out here. The mass percent of carbon is 79.1%. So 79.12% carbon mass. Okay, what's the molar mass of testosterone? Well, 17 atoms of carbon in one molecule, right?
Or 19.
19, excuse me. 19 atoms per molecule. Okay, we need to end up with grams per mole. That may not be enough room. Let me stretch it over here. 19 atoms per molecule. Okay. We need to end up with grams per mole. All right, this is atoms of carbon. Carbon, we know carbon is 12.01 grams per mole of carbon atoms. So we could get the mass out of that, out of carbon. Let's see, I may be jumping the gun there. If this is per molecule, why don't we get the moles first? Moles. Oops. Molecules. There we go. Per mole. Now we got our moles. Now we need to convert this to grams of compound. Somehow. If 19 atoms of carbon, we can find out the mass of carbon in a molecule. Atoms of carbon per molecule. Okay. 19 atoms would be 6.022 times 10 to the 23rd atoms of carbon per mole. That gets rid of both of them, doesn't it? Of carbon. And this would be 12.01 grams of carbon per mole of carbon. Okay, so now we have that many grams of carbon, but that only represents 79.12% by mass. So what we have here is 79.12 grams of carbon per 100 grams of compound, correct? That's what that means. I just flipped it. So let's see if that does everything for us. Atoms of carbon, atoms of carbon, atoms of carbon, moles of carbon, moles of carbon. This is moles of molecule, moles of compound. All right, we want to keep that one. It's not canceled. And then grams of carbon, grams of carbon. That should do it. So let's see if it works. 19 and, oh, these cancel. So we don't have to use that big number. 12.01 times, and then 100 times and 79.12 divided. 288.41. Is that even close? Yeah.
Atoms and molecules can be like canceled out or like count as the same unit.
Oh, we're canceling just the numbers. Yeah, yeah.
Okay.
We did one conversion using the Avogadro's number, and then with another one using Avogadro's, but numerator denominator cancels out. Right. I mean, what would you get if you divide them? 1. So I don't even know if I worked it the same way in the work problems. I was just flying by the seat of my pants. All right. Yeah, we're still in chapter 3. That's pitiful.
Dr.
20
Fly, quick question.
Sure.
Is the exam always 90 questions?
The exam?
Yeah.
Oh, no, it varies.
Okay, but I just wanted to get an idea, like, is it around 90 all the time, or like, is it somewhere around that number? Does that make sense?
No, I can't claim that either.
Oh, okay. Okay, I just wanted to know. That's okay. Thank you.
I can say one thing for sure. It's not as big as the review document.
Okay, perfect. Perfect. Thank you so much.
The review document has lots of similar type problems in it, just to give you a lot of practice.
It was good practice. Thank you. Thank you.
Okay, 24. I try to gauge it so, you can do it in an hour. Yeah. Some students struggle longer, but that's personal preference.
Gotcha. Thank you for clearing that up.
In your bright space, I think you actually have how many questions on each quiz? Because the first one was whatever out of 90. And
Yeah.
I think the second one is obviously like, because we haven't taken it yet, out of like 45.
Number of points.
Number of points. Okay.
Yeah. Sometimes, probably the first exam was 1 point per question. I think
Okay.
that's typical. But later on, when there's a difficulty differential, some might be worth more points than others.
Okay.
Okay, 24. Let's see. The oxide of iron has a formula Fe3O4. Fe4. Okay. What mass percent of iron does it contain? All right. So we know what to do here. Just assume you have 1 mole of that compound, and 3 irons would be 5585. 585 per mole. That would be 3 moles of iron per molecule or per unit, formula unit. And then 4 times 16. That's total mass of 1 mole. So 585 times, and then 64. So this is 231.55 grams per mole of compound. And the question was, what's percent mass of iron? So we go back to iron. This part is in the numerator again. 3 times 55, 85 is in the numerator. And in the denominator, we include everything. Times 100. All right, so I have to calculate that one again. That's 167.55. 167. Then divided by this number. Times 100. So that's 72.4% iron by mass. You may not have caught up on this problem, but if you try to balance charges, this is an ionic compound. That's a metal nonmetal. So if we say oxygen is -2, that's a total of -8, isn't it? Okay, how are you going to get a +8 out of those three? Right, each one would have to be 8/3 positive charge. Here's what actually happens. This is not a pure compound. I mean, it's an analysis of a purified version, but there are actually two compounds in here, two formula units. One is Fe2O3 and the other is FeO. That's a combination. So you got a +2 valence for this one and a +3 for this one. It's a mixture, actually. But the calculation still works. Let's see, number 26. Ammonium chromate, and kind enough to give you the formula. Contains what percent nitrogen by mass? I'll just set this one up. If we have this ammonium and then chromate, percent nitrogen by mass. So what you would want is in the numerator, you would want 2 times the nitrogen. Right? That's all the nitrogen that you have in this nitrogen. Yes. Okay, then down here, you would have it again. Plus 8 hydrogens. Plus 1 chromium, which is 51, actually 5200 rounded off. Okay, and then 4 oxygens times 100. That's your calculation. And you should come up with 18.4% nitrogen. Okay. All right. What's next? 30. A hydrocarbon, which is another way of saying a compound that consists of only hydrogen and only carbon. Think gasoline in your tank. That's a hydrocarbon. Or asphalt on the road. That's a hydrocarbon. Or actually, it's a base hydrocarbon with lots of other stuff in it. It's found to be 85.6% carbon by mass. 85.6% carbon, and the rest is hydrogen, which would be what? 14.4. See, 10, 10, 10. That's it. Okay, so that's the analysis of our compound. What's the empirical formula for this compound? Okay, remember what the empirical is? It's the simplest whole number ratio. And we can do that with just this information. Now, if we need the formula mass or the molar mass of the compound, we need one other piece of information. What is the molar mass of the compound itself? I didn't say that right. If we want to know the molecular formula, we need the molar mass of the compound. But we can do the empirical with just this.
I mean, I guess would you assume there's 100 grams?
Yeah, because you can't calculate with percent. That's a dimensionless number. So, but we assume that it's mass of carbon per 100 grams. So why just use a 100-gram sample? A 100-gram sample means 85.6 grams of carbon, 14.4 grams of hydrogen. Now we can convert to moles. and get the mole ratio because that's what we're after. Let's see, carbon would be 12.01 grams per mole, and hydrogen would be 1.01 grams per mole. And rather than string out the calculation, since we have to do some, we have to manipulate the ratio. Once we find out what the molar ratio is, that's fixed, and we just manipulate the ratio to get whole numbers. This is 7.13. I did that right. Let me do that again. 85.6, 12.01. Yeah. 7.13. And that's moles. And then 14.4 divided by 1.01 is 14.26 moles. Okay. So what's the next step? We try to work our way toward whole numbers. And the simplest way is to divide everything through by the smallest number. Remember, once you have a ratio established, if you multiply or divide both parts of the ratio, you haven't changed the ratio. So if we divide through by 7.13 here, that's 1. Divide by 7.13, that's 2. So our ratio is carbon 1 and hydrogen 2. That's the simplest whole number ratio. Right. 32. The empirical formula of styrene is CH. Styrene. Everybody's heard of styrene, right? Polystyrene. Like coolers. The really cheap coolers you can buy at Walmart, they're polystyrene beads. But styrene itself, don't ask me to write the molecule because I haven't looked it up lately. Its molar mass is 104.1 grams per mole. 104.1 grams per mole. That's for the molecule. That's molecular. The empirical, for comparison, is what? 12.01 and 1.01. 13.02 grams per mole of the empirical formula. So what are we looking for? We're looking for a multiplier. Okay. So if we multiply this times 10, that's too big. If we multiply it by 5, that would be 65. It's not big enough. So the simplest way to deal with it is to take that and divide it into this. And find out what that ratio is. Is it 8? Okay. Approximately 8. So that means this is equal to 8, and our formula then is 8H8. Let me see, maybe I can do it. I know it's got a benzene ring in it. And I think it's C. That's 1, 2, 1, 2, 3, 4, 5, 6. I need 2 carbons out here. And hydrogens, I've got a hydrogen here, 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 here. 5, that's 5 of them. I need 3 more hydrogens out here. So what if I do one there and 2 here? That's 1, 2, 3, 4, 5, 6, 7, 8. I think that's it. And each one of these is a carbon. So I think styrene is this benzene ring with a double bonded carbon group on the side. And that's where the polymerization takes place on these carbons. With benzene, you have this long chain of carbons with these benzene rings sticking out here in space. Take organic and we'll talk about it in a point. Okay, let's see. Adipic acid, 33. Adipic acid is a fatty acid, right? It's one of those carboxylic acid groups that gets attached to glycerol, right, to make a true fat. If you have three of them, you have a triglyceride, which is a true fat. And everybody's, when you get a full metabolic panel, blood work, it'll give triglycerides. They're just saying how much fat's in your blood. Let's see. Adipic acid, 49.32% carbon, 4384 oxygen, and 6.85 hydrogen. Hydrogen. Okay. All right, we've done an empirical formula before. You know how to do this. If you're only given percent by mass, you just assume 100 grams. Make this into grams, grams, grams. Use the molar mass of each one to convert to moles. That gives you the molar ratio of each one in the compound. Then you work your way through by, first you divide by the smallest one. That gives one of them is equal to 1. And the others, usually they come out as either something and a quarter, something and a third, something and a half. Then you get rid of the fractions by multiplying through by whatever will do that. We don't need to do it, do we? Okay. Because I'm running short of time as usual. Let's see. Vitamin C, also known as ascorbic acid.
We're going to have access to the key, correct? For the ones you don't get to, we'll be able to work them out ourselves.
Oh, yeah. Yeah.
Okay, perfect.
It's in Brightspace. Yeah.
Okay, perfect.
You'll have the review document, and then there'll be another document called the key, has all the answers.
Okay, perfect.
And then you'll have one that's a PDF file of my handwriting.
Oh, okay.
Working the problem out.
Okay, perfect.
And we'll probably do the same thing with this vitamin C. For the vitamin C, you go one step further. You find out what the empirical formula for vitamin C is. Then you write the, let's see, this is 34. It's carbon, hydrogen, and oxygen. So you'd have something, something, something here, and that would be an N. And this would be X, Y, and Z values of some kind in the empirical formula. Then you calculate the empirical weight for this. And then if you're given the molecular weight, 180 grams per mole, then you take this empirical weight and ratio it. And that value here equals that. The nearest whole number equals that. Multiply this through, and that's your molecular formula. If we have time, I'll keep this one on the side. This is chapter 3. We'll come back and do the whole thing, but I want to get through chapter 4 before I run out of time. And if I do run out of time, usually what I do is just keep talking and you guys can go do what you have to do. And I'll record it. How many of the following are true concerning balanced chemical equations? Well, the number of molecules is conserved. No. What does that mean? The number of molecules is conserved. That means the sum of the coefficients is the same on both sides, because the coefficient tells you how many molecules on each side. For instance, if we say, if I say hydrogen plus oxygen yields water, and we balance that equation, how many molecules on this side? 3. How many on this side? 2. Right. You just need one example to blow that one out of the water. Now this ratio becomes useful later when we talk about Le Chatelier's principle. But as far as Roman numeral 1 goes, that's false. We don't conserve the number of molecules. We conserve the number of atoms. Wait a minute. How many of the following are true concerning balanced chemical equations? Oh, A is 1. How many are true? I threw myself a curve there. Okay, so A through E is 1 through 5. How many of them are true? So Roman numeral 1 is false. How about 2? The coefficients of the reactants tell you how much of each reactant you are given. That's a little misleading. When we say how much, we usually mean mass. So that's why I'm saying that Roman numeral 2 is false also. Atoms are neither created nor destroyed. There we go. That one's true. 4 says the coefficients indicate the mass ratios. Mole ratios. False. And then number 5 should be false also. The sum of the coefficients on the reactant side equals the sum product side. That's another way of saying 1. Right, and they're both false. So we only had one that was true. It helps to read the question occasionally. Even for your instructor. Or especially for your instructor. 37. In balancing an equation, we change what to make the number of atoms on each side of the equation balance? Coefficients. Yeah, coefficients. All right. Did we just get into chapter 4 and I missed it? Do we balance? No, we balanced equations in chapter 3. Okay, never mind. What's the coefficient for oxygen when the following equation is balanced? All right. I'll work through this one completely. NH3, these are all gases, so I'm not going to put gas in there. And then NO2 and water. Okay, budget method. What elements do we have? Nitrogen, hydrogen, oxygen. We have 1 mole on this side. We have 3 hydrogens. We have 2 oxygens. On this side, we have 1 nitrogen. Hydrogens, we have 2. And oxygens, we have 3. Okay? So, first trick, don't mess with that one yet. Leave oxygens alone. Leave them till last. So we could do nitrogen's already balanced, so our only other choice is hydrogens. So if we have 2 on that side and 3 on this side, what's the magic phrase? Cross multiply, yeah. So let's bring this 2 over here and this 3 over here. And that works only if hydrogen occurs in one place. Right? If it occurs in multiple places, then it gets a little more complicated. But it will work, cross multiply will work if hydrogen only occurs on one side here, one place on this side. All right, if we do hydrogens, then we should have 3 over there, right? And 2 over here. Okay, so that gives us 6 hydrogens, 2 nitrogens, 6 hydrogens, yes, and 3, 4, 5. 5 oxygens, correct? Let's see. Yeah. Okay, so now we can do nitrogens with a 2. And that changes the oxygens to 7, correct? Okay. Now we can use our other trick, fractional coefficient. Because how are we going to get 7 oxygens on this side with an even numbered molecule? Can't do it in one step. Let's do 7 halves. That gives us 7 here. Okay? So then, to get rid of everything, get rid of the fraction, we multiply the whole thing through by 2. Because 2 times a half is a whole. That gives us 6, 4, 7, and 4. Now, the only reason I went to that trouble, because to answer the question, all you need to know is that, all right, so I'm going to multiply the whole thing by 2. That gives me 7 oxygens. I got the answer. But suppose I'm sneaky and I ask you for a different one. Like, what's the coefficient of water? Then you need to go through the whole thing. Thank you for catching that error. All right. What's the sum of the coefficients of the following equation when balanced using smallest whole numbers? This one looks challenging. I'm already out of time. I'm past time. I'm not even in chapter 4 yet. Okay, if you have to go, yeah, you won't hurt my feeling. If you can stay, fine. We'll just keep plugging away. All right, I think we better do this one because it looks to me to be an interesting one. NH2, NaNO3, and NaN3. It can fool you though. It can look bad, not really be bad. Na. Okay, now let's see. We can't use polyatomic ion trick because the groups with nitrogen in them, they're gonna get busted up. See? So that won't work. All right, so let's go to the budget. And I don't think this wouldn't be a candidate for oxidation reduction because it's in chapter 3. So I'm not even going to go there. Let's see if we can do it the budget method. So sodiums and nitrogen and hydrogens and oxygens. And that's everybody. So we got 2 sodiums. We got 1, 2 nitrogens, hydrogens, 2, and oxygens, 3. Let's see, that's 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 2 sodiums on this side. Nitrogens, 3, and 1 is 4. And hydrogens, 1 and 3 is 4. And oxygens, 1. I think I got that right. 4, 5, 6, 7, 8, 9, 10, 11. 5, 5, 6 is 11. Okay. So where do we start?
Did 3 NaOH on the reactant side. Or on the product side. That was step 1.
We did 3 here.
Yep.
Now, why would I do that? Oh, to give me 3 oxygens. Okay, so we're going backwards to what I thought. We're doing oxygens first. Okay, that gives us oxygens. That gives us 3, 4 sodiums. And 3, 6 hydrogens. Okay. So now, did I go to one of these?
Yep. So that one,
This one?
yep. And that was a 3,
I put a 3 there?
yeah. And that gave us,
It was 4 sodiums.
yeah,
Okay. And it gave us 4 nitrogens and 6 hydrogens. Oh, that was too easy. Okay. If you see one like this, again, it better be an extra credit. Because that's too much for a beginning chemistry student. If your instructor can figure it out. All right, let's see. Oh, we still got another one. When this equation is balanced with a small set of integers, okay, 43. The reason I put 43 there is actually, yeah, the sum of the coefficients for this one. C6H14, that's another hydrocarbon. We got a combustion reaction going on here. Okay. So carbon, hydrogen, oxygen. This is 6, 14, and 2. This is 1, 2, and 3. Yep. For this type of combustion, I start with the carbons. 6, and that's 12, 13 oxygens. Okay. Then I go to balance the hydrogens. We got 14 here. I need a 7 there. And that makes 7 plus 12 is 19. Correct? Okay. Then we use, in order to get 19 on this side, I use a fraction. And then I get rid of the fraction. So we're going to multiply the whole thing through by 2. There, 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 there. Then add up our coefficients. Let's see, 11, 13, 17, 15, 17, and 47, right? Yep, 47. Oh my goodness, I shouldn't have picked so many. Question?
yep, so, okay. 14.
Oh, 14, 12,
12,
19.
Okay.
I went backwards.
Okay.
That's okay. Let's see. A reaction occurs between sodium carbonate and hydrochloric acid. 4. Sodium carbonate. You have to be able to write this. That's a 2 minus. This is a 1 plus, so we need a 2 there. Sodium carbonate and hydrochloric acid.
Okay, so now we're in chapter 1.
Are we?
Yeah. Yes, sort of chapter 4, on question number 4. I'm going by,
No, I don't think we've made chapter 4 yet.
okay, you know, I'm gonna be crazy, okay, go ahead, sorry.
Wait a minute.
No, no.
Yeah, because it restarts numbering. Hopefully chapter 4 won't have as many problems in it. 44. There we go. To make carbon dioxide and water. So we're telling you what the outcome is. Actually, doesn't make just that. It makes sodium chloride plus carbon dioxide and water, right? Yeah, the correct coefficients respectively for each one. Okay. These acid-base reactions are usually fairly well behaved. Now, this is a base. We're going to find out more details about that in the second semester. But this will, if you put sodium carbonate in water, dissolve it in water, it will be basic. So, if we have sodium, let's see, carbonate gets busted up, so we can't keep it as a balancing unit. So we have to go sodium, carbon, oxygen, hydrogen, and chlorine. So 2 sodiums, 1 carbon, 3 oxygens, 1 hydrogen, 1 chlorine. On this side, we have 1 sodium, 1 carbon, oxygen, 3 oxygens, and 2 hydrogens, and 1 chlorine. Okay, I would start with sodium. I just say 2 in here. That gives us 2 chlorines. Now we have to come back over here and make 2 chlorines and 2 hydrogens. And lo and behold, we're balanced. All right. Let's see, 45. All right, this takes a little sleuthing. Chemical reaction has the equation 2A plus B yields C. 2A plus B yields C. So 2 moles of A, 1 mole of B, 1 mole of C is the product, or 2 atoms of A or 2 molecules of A, whichever the case may be. In this case, we got circles with letters in them. So 2 A circles and a B circle. What's the question? Which of the following figures best illustrates a stoichiometric ratio of A and B? When we say stoichiometric ratio, we're talking about before the reaction occurs, we have 2 A circles and 1 B circle ratio. So if we look at each one of these, and we say which one has 2 A's for every 1 B? 3, 4, 5, 6, 7, 8 versus 4. Roman numeral 1 does. That's a stoichiometric ratio. How about 2? Let's see. 2, 2, 2, 2, 2. That's a 1-to-1 ratio, so 2 is not it. How about 3? It's the other way around. 2 B's to every A. That one's out. And 4, you can't have a stoichiometric ratio with C. They got C in there with it. So that's out also. So the only one that works is Roman numeral 1. That figure represents a stoichiometric ratio. 46. Uh, 7.11 gram sample of potassium chlorate. Potassium chlorate. And this is a -1 charge, that's a +1, so that's the molecule. And 2 of them yields 2 potassium chlorides plus an oxygen. 3 oxygens, excuse me. 3 oxygens. How many moles of oxygen are formed if you start with 7.11 grams of this? 7.11 grams. So if we're looking for moles, this has to be converted to moles before we can get to that side. Right? So what we need is molar mass. Potassium is, let's see, 39.10 rounded off. 39.10. Chlorine is 35.45. And 3 oxygens is 48. 5, 13, 2. See, is that right? Yeah. 2, 5, 8, 12. 122.55. So that'll give us the number of moles of potassium chlorate. 7.11. That's 5.80 times 10 to the minus 2 moles of potassium chlorate. Now we need to convert that to moles of oxygen, and that'll give us our answer. So the ratio is, we're going to cancel this one, so we need a 2 down here. And the oxygen has a coefficient of 3. So 1.5 times that should do it. 8.70 times 10 to the minus 2 moles of oxygen. Oh, standard notation. All right, so 2 positions. 1, 2. So 0.087 moles. D. Like everybody's gone. 47. How many grams of calcium nitrate can be produced by reacting HNO3 with 6.33 grams of calcium hydroxide? All right, so calcium, the reactants are calcium hydroxide and nitric acid. Yes, HNO3. To yield calcium nitrate. That can't be everything. It has to be water. Remember, acid-base reactions always produce a salt and water. So we're going to combine so many hydrogens with the hydroxyls to make water, then the calciums combine with the nitrates to give us that. Yeah. Okay, so we need to balance this equation. Let's see. Well, calciums are already balanced. What we need, if we've got 2 hydroxyls, how many hydrogens do we need? We've got 2 of these, we need 2 of those to make 2 waters. So this needs to be a 2, and this needs to be a 2. Yep. I sort of skipped the budget method on this one. But you can confirm it if you want to work the budget method. Then the question is, how many grams of calcium nitrate are produced? 6.33 grams of calcium hydroxide. 6.33 grams. If you're only given one compound, one absolute amount, then the other one has to be excess. Because how much can be produced from this? Well, you got to have enough of that. And they didn't say, so we have to assume it's excess. All right, so now we just convert this one by using the molar mass of calcium hydroxide. And let's see, calcium is 40, is it? 40.08 for calcium. 2 oxygens is 32, and 2 hydrogens is 2.02. So that's, let's see, 0, 1, 44.1. Oops. 44.10. And 6.33 and divide 44.10.
74.1.
74?
Yeah.
Oh, yeah. I'm not thinking. So let's do that again. 6.33, 74.10. There we go. 8.54 times 10 to the minus 2 moles of calcium hydroxide. Now we want to convert that to how many grams of calcium nitrate. So we got to find out how many moles. Well, fortunately, the ratio is 1 to 1. So this is also calcium nitrate. But we can't convert it until we do molar mass of calcium nitrate. So calcium's the same. Nitrogen's different. How many nitrogens do we have? 2. So 1401, yeah, 2802 is the nitrogens. And 6 oxygens. 96. Okay, and then 2802 plus that and 40.08 plus that. 164.1. Okay. So we need grams on the top. Cancel the moles on the bottom. 164.10 times that value. And I've got both of them in my calculator. So I just hit the multiply button. And that tells me 14.02 grams of calcium nitrate. Nearest one is 14.0. Let's see, 52. Snuck another one in chapter 3. For this reaction, what mass of P4010 must be consumed if so many molecules of water are also consumed? All right. P4010, water, and the equation is balanced. 4H3PO4. We're looking for mass here, right? And we're given 3.71 times 10 to the 23rd. 10 to the 23rd molecules. That has to be converted to moles. And that's 6.022 times 10 to the 23rd. I got 0.616 moles. This one. Of this one, actually. Moles of water. So the ratio is 6 to 1. I want to get rid of water, so it has to be in the denominator. And we have 1 P4010 for every 6 waters. So I divide that by 6, and that's 0.103 moles of P4010. And it asks for grams, isn't it? Okay. So now we have to go molar mass. Phosphorus is 30.97 times 4. And then 16 times 10 is 160. So I get, well, that can't be right. Hold on. There we go. 190.97. Know what you got?
You got 283.88
Where?
on the, where you worked it out.
Huh.
So people roads in 430.97, 10 of 16.
Let's try that one again. 3.71. Enter.
Yeah, 283.88.
For this one? Or for the final answer?
The molecular weight of people road 10.
Okay.
You solved it differently on the.
Yeah, 283.88. You know what I forgot to do? I forgot to multiply 4 times.
Okay.
Okay, now times 0.103 is 29.2. Close enough, 29.1. That's probably got a rounding error. Good thing I don't have to take my own exams.
Yeah, that's better than my math there.
Oh, another one. Let's see, 58 according to the equation to give 3, what's the percent? Oh, percent yield. All right, 58. This one's not as complicated as you might think because there's a lot of blue smoke here. 5.95 gram sample of silver nitrate is reacted with the barium chloride. We do have to do it. 2 silver nitrates plus barium chloride, okay, yields 2 silver chloride. So that's our precipitate. And barium nitrate. This is aqueous, this is aqueous, and this is aqueous. And we're balanced. Okay, 5.95 gram sample of silver nitrate. 5.95 gram sample. Silver nitrate, so we'd have to dissolve it in water first. And gives us 3.17 grams of silver chloride. Chloride, actual. What we're asked to do is calculate the percent yield. So what we have to do is find out what's the theoretical yield of this going to that with this excess. So we need the molar mass of silver nitrate. Silver is 107.87. Nitrogen is 14.01 and 3 oxygens is 48. 8, 19, 6, 169.88. So that'll give us the moles of silver nitrate. 88. And that's 3.50 times 10 to the minus 2 moles. Actually, it's 2 to 2 or 1 to 1. So this is also the moles of silver chloride. Theoretical. We just have to convert it to silver chloride now. Moles on the bottom, grams on the top. So silver is still 107.87. And Chlorine is 35.45. That's 12, 112 is 13, 112 is 13. 143.32. Three, two times, and that gives us 5.0197. I'm just going to carry it out. Moles of, grams, grams of silver chloride. That's the expected amount. So the percent yield is 3.17 divided by 5.0197 times 100. And I get 63%. 63.2 actually. Okay. 59. What mass of carbon tetrachloride will form 1.2 moles of methane react with 1.11 moles chlorine? Okay, so this is a limiting reaction problem. So I'm going to have to do this one. Limiting reactant. $59. Okay, we've got a methane and chlorine reaction. Bet that's a doozy. It'd be exothermic. Oops. Hydrogen chloride gas would be toxic too. Do this one under a fume hood. Okay. 4. Okay, so that's balanced. And we're starting with what mass of carbon tetrachloride will be formed? What mass will be formed if 1.2 moles of methane react with 1.11 moles of chlorine? Okay. Normally what I would do is say, how much can you get from all of this and how much can you get from all of that? But I think since we're given moles, if we use all of this, it's going to take 4.8 moles of chlorine, isn't it? Because it's 4 to 1. So that's the limiting one right there.
Okay.
Right? Okay. So we can just go straight from this one to, this is chlorine, and get rid of chlorine and leave us with carbon tetrachloride. So divide that by 4. Zero 0.2775. Yep. Moles of carbon tetrachloride. Then we can convert it to grams. We just need 12.01 for the carbon and 4 times 35.45 for the chlorine. I get 153.81 grams per mole. So this one needs moles on the bottom, grams on the top. 153.81 times 0.2775. So I get 42.7 grams of carbon tetrachloride. All right. Never ending. Chapter 3 doesn't want to turn us loose. Which of the following statements is always true concerning a reaction represented by the following balanced chemical equation? So we got 2 ethanes plus 7 oxygens yields 6 waters and 4 carbon dioxides. If we have, oh, okay, I better write this one up here. C2H6 plus 7 oxygens yields CO2 in water. And this is 4, I put them backwards. 6 there. Okay, so we're going to have to look at each one of these. None of these statements is true as the last one. That means we got to look at all of them. So if we have equal masses, there is no limiting reactant. All right, let's look at the stoichiometry. We know that 2 moles of ethane reacts with 7 moles of oxygen. If that were the case, what would that mass be? If we converted this to 2 moles of C2H6 and 7 moles of oxygen, what would that be in grams? That would be the mass ratio. Right, so let's see, 24.02 for the carbons and 6.06, right, for the hydrogens. 30.08. So this is 30.08 grams. If we go 2 moles of that. Oops, no, it isn't. It's 60.16. Right? Because that's 1 mole. 60.16 grams. Okay, oxygen is 32 grams per mole, and 7 times 32. 224?
Yep.
That's 224 grams. So that's the mass ratio. That's the stoichiometric mass ratio for this equation. Now, if we have equal masses of these two, there is no limiting reactant. That's false. Because equal masses, this is the stoichiometric ratio. Equal masses would not be stoichiometric. Okay. B, if we have an equal number of moles of C2H6 and O2, there's no limiting reactant. Equal number of moles is not the mole ratio. It's 2 of these and 7 of those. So B can't be it either. If we have more mass of C2H6 than O2, then O2 must be limiting. If the mass of C2H6 is greater than, what that's saying is greater than the mass of oxygen, then oxygen is limiting. That's true. Because if we had, say, 225 grams of this one, it would definitely use up all of that, because that'd be 4 times this, and this would be gone before that one's used up. So C is correct. D, if we have more mass of O2 than C2H6 must be limiting. That's just the opposite of C, and you can't have both. Right? So we do have one that is true. That's C. That took a little logical interpretation. All right. Let's see, 62. 62. What is 62? Equal masses of hydrogen gas and oxygen gas are reacted to form water. Which substance is limiting? Okay. So we need a balanced equation, and we've done this one before. Hydrogen and oxygen together. Hydrogen, oxygen yields water. Right, we need 2 of those and 2 of these. So this mass would be 32 grams. 1 mole. 2 moles of this would be 4.04 grams. That's the stoichiometric ratio right there. Okay, now if we say equal masses of hydrogen and oxygen are reacted. So if the masses are equal, say if this were 32, right, then that one would be used up because this one would have plenty. We only need 4 grams of this one. So if we have 32 of this one, oxygen is limiting. So A is correct. Oxygen is limiting. Not more information is needed. Oh, we found our answer. That's it. Oxygen is limiting if we have equal masses. Say we have 32 grams here. Right, that's plenty. That's 8 times as much as you need. So oxygen runs out first. I wouldn't want to be in that rocket. It might not make it to orbit. Okay, 64. Get rid of this thing. For the reaction, nitrogen plus hydrogen yields N2H4, dinitrogen tetrahydride. Actually, there's a special name for N2H4. I think it's hydrazine. Yeah, there it is right there, hydrazine. If the percent yield of this reaction is 82%, what's the actual mass of hydrazine produced when 25.57 grams of nitrogen reacts with 4.45 grams of hydrogen? Okay, so we got this equation, 2 hydrogens yields hydrazine. There we go. What's the percent? Is the percent yield is 82%. Percent yield equals 82%. Okay. What's the actual mass of hydrazine produced when 25.57 grams of nitrogen reacts with 4.45 grams of hydrogen? All right. So in this case, I would do my usual. I would say, how much hydrazine do we get if we react all of this? How much do we get if we react all of that? So we need moles of nitrogen. That's 28.02. It's 0.9126 moles of nitrogen, and the ratio is 1 to 1. So that's also equal to 0.9126 moles of hydrazine. This one would be 2.02 grams per mole for nitrogen, like 2 times 1.01. So 4.45 divided by 2.02 is 2.203. 2.203 moles of hydrogen, and we would convert that to hydrazine. 2 hydrogens and 1 hydrazine. Right? Ratio of 2 to 1. So 2 divided into that is 1.101. 1.101. So that means that nitrogen is limiting. And it will we'll only, out of this reaction, we'll only produce that much hydrazine. Okay, so theoretically, we would produce how much hydrazine? We would convert moles to grams, right, of hydrazine. So 14.01, 28.02 for the nitrogen, and 4.04 for the hydrogen. is 3206 times 0.9126. And I get 29.3 grams of hydrazine. Theoretical. Okay. So if we go to our formula, percent yield, 82% yield equals what we actually get from this reaction. Which is our unknown, right? What's the actual mass, right? So that's our unknown. Actual divided by the theoretical, 29.3 grams times 100 yields percent. Okay, so that's on top. If we flip this over here, 82%. This is in the numerator. Now it becomes in the denominator. And this is the denominator. It becomes the numerator. 3. Then we divide 82 by 100 and multiply by 29.3. So that's 24.0 grams of hydrazine. B. That's known as a multi-step problem. Did I lose you? No? Good deal. Moving on.
They do that because I think they is 29.2. So if you didn't take the extra step, you got
Oh.
in theory.
Yeah. Yeah. Oh, yeah. That's the nature of multiple choice questions. Those who create them try to anticipate the mistakes and put the answer in that would follow from that mistake. So if you figure it wrong and you see your answer there, you think it's right, but it isn't. 66. What's the molar mass of tetraphosphorus decaoxide? Tetraphosphorus decaoxide. So 30.97 for phosphorus and 10 times 16 for oxygen. That'll be, let's see, in about 122, something like that, maybe 282 or something like that. 284. All right. I did it to myself. I picked all these out. Okay, which of the following samples contains the greatest number of moles of carbon atoms? Okay. Henry Ford coming up. So we got 58 grams of C4H10. C4H10. 58 grams. And then C2H5OH, which is ethanol, 6 grams. CO2 is 44 grams. And C6H12O6 is glucose. Actually, it's a hexose. We don't know if it's glucose or not. Depends on its structure. Could be fructose. Let's see. All contain the same number. All right. What's the question again? Which of the following samples contains greatest number of moles of carbon atoms? All right. So we need to convert these each to moles of the compound and then account for the carbon atoms. So C4H10, so 12.01 times 4 is 4804, and then 10 times 1.01 plus that is 5814. 5814. While I've got it in here, let me just, well, that's essentially one. That's 1 mole of compound. How about 12.01 and 5.05 and then 16 and then 1.01 again? It's 3407. Divided into 46 is 1.35. That's just of the compound.
Got two
I'm sorry.
carbons. So it'd be,
Oh, you're going ahead.
no, I mean,
That's fine.
'cause that's,
This is 1 mole of compound times, let's see,
oh no, I was on B as well, cause it should be 4608, not 3407.
oh,
4608,
46.
yes, cause two carbons,
Oh, okay. I forgot
Yeah,
to multiply those.
yeah. 6.
Okay, so that's 1 again.
Okay.
Times, and this ratio is 2 to 1. That equals 2 moles of carbons. How about CO2? Can I get that one right? 44. I see where they're going with this one. Times, this is 1 to 1. Equals 1 mole of carbon. And I bet this one is 180. So that's 1 times 6 to 1. 6 moles. There's your answer. All right. 70. An unknown molecule is found to consist of 24% carbon, 4% hydrogen, and the remaining chlorine. What's the molecular formula of the molecule given that molar mass? Okay. I mean, I can do this one, but I think the class should be able to handle this one. Right? You just calculate the, if you have 24% carbon and 4% hydrogen, and the rest is chlorine. So if this is 28.2, that's 817, 71.8% chlorine. And you just figure the empirical formula and then use the molar mass is found to be approximately 150. And you try to find the multiplier. Right? You're going to have carbon, hydrogen, and chlorine. You try to find the multiplier. You find out what's this mass right here, and then compare it to the molecular weight and say what factor would make this one equal to that one. It's either 1, 2, 3, 4, whatever. That's where you go with it. Answer should be C3H6Cl3. Does it say what that is? No, it doesn't. Probably an insecticide of some kind. Okay, naturally occurring iron contains so much percent of 54 iron, 91.66% of 56. So in this case, we are actually given the atomic masses for each one of those isotopes. So the first one is 53.9, second one's 55.9 and 56.9, and then 57.9. And you just take the decimal equivalent of each one of those percentages and multiply it times the value and add your results together, and you should get 55.85. All right, this one should go quickly. 73. The empirical formula for each one of these representations. All right, so you just count up. The first one is 6 carbons and 6 hydrogens. A, B, C, D. Yeah, all only to D. Well, yeah, we'll do all of them. So the first one is C6H6 is the molecular. So the empirical would be CH11. The second one is C2H4. So the empirical would be CH2. The third one, I have to really do some counting here. Carbons, 1, 2, 3, 4, 5, 6 carbons. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. And I bet 6 oxygens if I count. Yep. So the ratio here is 1 to 1. And the last one has carbon, hydrogen, and oxygen. How many carbons? 1, 2, 3, 4, 5, 6. Hydrogens.
10.
2, 4, 6, 10. Okay. And 2 oxygens. So that'd be C divided by 2. That'd give us an O1. So divide by 2 would be 5, and divide by 2 would be 3. There you go. Those are your empirical formulas. We skipped a few. Okay, now we're chapter 4. All right, number 1. An unknown substance dissolves readily in water, but not in benzene, which is a nonpolar solvent. Molecules of what type are present in the substance? If it dissolves in water, but not, like dissolves like. So the substance dissolving, the solute must be polar, because water is a polar solvent. And whatever the substance is dissolves in water, but not benzene. All right, so the polar substance, this polar solute, doesn't like the nonpolar solvent. So that would be B. Who's next? C? C. Excuse me. 5. What if the answer happens to be C? Which of the following is not a strong base? Okay. All of the alkaline metals and alkaline earths produce strong hydroxides. Those are the bases. So, which is not a strong base? Calcium hydroxide strong, potassium hydroxide strong, lithium, strontium, they're all strong. Ammonia is not. Ammonia is a base. It just doesn't have hydroxyls in the molecule. Now, we'll have to explain that next semester, but I'll give you a taste. What we end up with, if we say the base is a hydrogen acceptor, you put ammonia in water, water becomes a reactant. So if you put ammonia in water, now water donates a proton. So water is the acid and ammonia is the base. It's the hydrogen's acceptor. Okay. So we end up with NH4 in an aqueous solution, plus what's left over. Take away 1 hydrogen, and it leaves its electron behind. There's your hydroxyl. Okay. That makes this, but this is weak. In other words, It wants to be over here, way over here. Produces very little of that. In fact, I did calculation one time. 99.6% is that. And you only have a little bit of this in that bottle of ammonia that you clean with. Okay, let's see. That was 5, 6. Starting to get weak. Which of the following is paired incorrectly? All right, A through E. So the first one, H2SO4 is a strong acid. Sulfuric acid is definitely strong. HNO3 is a weak acid? Nope. That one's bad. HNO3 is a strong acid. Strong base, barium hydroxide? Yes. Strong acid, HCl, hydrochloric acid? Yes. Weak base, ammonia? Correct. So the bad one is B. Nitric acid is a strong acid. 7. Let's see. The man who discovered the essential nature of acids through solution conductivity studies is Arrhenius. I don't think we mentioned that in class. That's in your textbook. Arrhenius is the one who was first investigating acid bases and their nature. In fact, he came up with a proposal that acids are those substances that produce hydrogen from their molecules, and bases are those that produce hydroxyls from their molecules. That's the Arrhenius definition. We were using the Bronsted-Lowry definition, which went one step beyond that to account for those things like ammonia. Ammonia doesn't have hydroxyl in it, right? So Arrhenius is this way. Bronsted-Lowry encompasses Arrhenius, plus it facilitates the understanding of other types of bases that Arrhenius couldn't. All right, let's see. Keep getting these pop-ups. 9. A 16.4 gram sample of HF or gram sample of HF is dissolved in water to give 2 times 10 to the second milliliters of solution. So this is and 2 times 10 to the second milliliters equals volume. What's the concentration in molarity? If we look at the answers, it's looking for molarity. This has to be converted to moles. So we're going to divide by 19. Like, yeah, 19. That gives us so many moles of HF. Which is 0.863 moles. This has to be in liters. So it's easier for me if it's in standard notation. This will be 200 milliliters, right? So move it 3, 0.200 liters. So if we divide this by the volume, we should get molarity. 4.3. 4.1. What did I do wrong? 16.4, 19, and then 0.2. I got 4.3. All right, that's the closest answer. That needs correction. That's an old document. I probably corrected it someplace else and forgot to do it here. It's okay?
Yeah. I was looking at.
Okay.
Let's see, 19. Fluorine is 19, hydrogen is 1.01, so it'd be 20.01
That's my mistake.
instead of 19.
Yeah, there I did it again. So 4.1 is correct. Okay, today, if something doesn't compute, you suspect the instructor. What mass of calcium chloride is needed to prepare 3.950 liters of 1.49 molar solution? Okay. So 1.49 molar is equal to moles divided by the volume, 3.950 liters. So if we multiply this one times that one, that'll give us the moles of calcium chloride that we need. Then we just have to convert it to mass. So I get 5.886 moles of calcium chloride. Calcium chloride. So we need molar mass. Calcium is 40.08. Chlorine is 35.45 times 2. Added together, 110.98. And this is going to be grams. Let's see, times, here we go. 3 significant figures. 653 grams. $16. What's the mass of the solute? What mass of solute is contained in 256 milliliters of 0.838 molar ammonium chloride? So we got, let's see, molarity times volume is moles. And if we use 0.838 molar, 0.838 molar, and convert the volume to liters, 0.256 liters, then we'll get the number of moles of ammonium chloride. This is 0.2145 moles of ammonium chloride. So now we need conversion factor. Nitrogen is 14.01, 4 hydrogens 4.04, and chlorine 35.45. That's 53.50. Times 0.2145, which is 11.5 grams. Ah, 17. .28 gram sample of barium hydroxide dissolved in enough water to make so many liters. How many milliliters of this solution must be diluted with water in order to make 1 liter of 0.1 molar? Okay, this is a multi-step problem. In order to calculate the stock solution concentration, we need the number of moles of barium hydroxide. 7428. That's our starting point. barium hydroxide, grams per mole. So barium hydroxide is this. Barium is a big atom, 137.33. And then 2 oxygens is 32 and 2 hydrogens is 2.02. So if I did my calculations right, that should be 171.35 divided into 74.28. And I get 0.4335 moles. We calculate the concentrated molarity is 4335 divided by the volume, 2.450 liters, moles per liter, 2.450. So this is 0.1769 molar. Oops. Okay. Now we have to do a dilution experiment. So we have concentrated, volume concentrated equals dilute, volume dilute. Which ones do we know? We know this one. And the question is, how many milliliters of that solution need to be diluted? So this is the unknown. To give us a molarity of 0.1 and a volume of 1 liter. Okay. So 1 times that is 0.1 divided by 0.1769. And I get 0.565 liters. Is it in liters? No, milliliters. So I'll move it 3 to the right, 565 milliliters. Okay, 18. What volume of 18 molar sulfuric acid must be used to prepare 2.3 liters of 0.145 molar? This is even simpler than the one ahead of it. So I would just say concentrate. We know it's a dilution problem. Molarity dilute, volume dilute. And put our values in here. So the concentrated molarity is 18. 18 molar concentrated. What volume? Unknown. So we want to end up with 0.145 in a total volume of 2.3 liters. Okay, and the answers are all in milliliters. So if we're going to have MC VC equals MD VD, solve for this one. Okay. If I want my answer to be in milliliters, I would change this to milliliters. Right, 2,300 milliliters. So this answer is going to be 0.145 times 2,300 milliliters divided by 18. And that'll give us an answer directly in milliliters. Okay, I get 18 and a half. Ooh, it rounded off to 19. Maybe I did something wrong. Let me check it. Oh, that's only 2 significant figures. Yeah, 19. That's the kicker. If I were doing this in the lab, I'd still go 18.5. Okay, let's see. Skip a few. Repetition. Okay, types of chemical reactions. 28. The following reactions are examples of what? We may know that the first one and the second one are certain types, but what do we have to choose from? That's the other question. So zinc bromide, silver nitrate yields zinc nitrate and silver bromide. Right. Is there any change in that first one for oxidation states? The zinc is a +2 because bromine is -1. How about the other side? Nitrate is -1. There are two of them, so zinc is still a +2. That didn't change. Bromine didn't change. How about silver? Silver and nitrate. Silver's 1+, nitrate's -1, bromine's minus. That one is not a redox. Okay, so we can say safely that redox is not one of them. Acid-base reaction. I don't see any acids or bases in this group. How about precipitations? Yeah, we got a solid formed in both of them. That's the only one. C. And we'll go to 29. So, oxidation reduction. Rule of thumb. We've got elements on one side, they're in compounds on the other side. First one is elements to compounds. Second one is compound to element. Third one is a combustion reaction. All combustion reactions are redox. So these are all three definitely redox reactions. They're not all combustion. The last one is, but we can't say that they're all combustion, so we can't include B in our answer. Right? It's only good for one of them. And there's no precipitation because you don't have an aqueous solution spitting out a solid. Right? So the only one that covers all three of them is oxidation reduction. Okay. That's the trick to that one. Not to be fooled by the third one, because all of them are not that characteristic. 32. Which of the following salts is insoluble in water? So you just have to look those up in in your chart. So we look up sodium and sulfide. Sodium and sulfide is soluble. In fact, all sodium salts are soluble. Potassium carbonate. All potassium salts are soluble. Lead nitrate. All nitrates are soluble. Right? And calcium chloride. Most chlorides are soluble. Calcium chloride is one of them. There are some chlorides that are not soluble, like silver chloride. So all of them are soluble. $37. Give that one a rest. Try this one. Consider an aqueous solution of calcium nitrate and sodium phosphate. What's the formula of the solid formed in the reaction? Okay, so if we're just trying to decide what's the formula of the solid, we just need to know which cation reacts with which anion. Calcium nitrate and sodium phosphate. Okay, so we break up into calcium ions, nitrate ions, sodium ions, and phosphate ions. So this sodium gets together with that nitrate and they're completely soluble. And this calcium gets together with that phosphate, and we look it up in our chart, that's sharp precipitate. So we got calcium 2 plus and phosphate 3 minus. Oops, that's phosphate. There we go. So we bring the 3 over here and the 2 over there. Ca3PO4 sub 2. All right. 38, 39, and 40 go together. And we have to write a balanced equation first. The formula equation for 38, based upon barium chloride plus silver nitrate. Oops, I keep doing that. Silver nitrate yields silver chloride solid plus barium nitrate. And that's aqueous. All right. Now I write my compounds correctly. 2 plus, yes, 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 and yes. Okay, balance. Bariums are okay. Chlorines are not. 2 of these, which means 2 silvers, which gives us 2 nitrates. That's it. That's balanced. Now, the question from 38 is, the balanced molecular equation contains which one of the following terms? First one is, and we have to say, we have to take into account coefficients, formulas, and states. So silver chloride with solid is not right for the first one. Second one is, because it has a coefficient of 2. So B is the correct answer for this one. 39 says which term is in the complete ionic equation. And so barium 2 plus 2 chlorines. Remember, when you break apart that ionic solid, the coefficient becomes, the subscript becomes the coefficient. 2 silvers, unless there's already a coefficient there, and then you got to take that into account too. Plus 2 nitrates. And then we'll swing around. The solid doesn't change. It's effectively removed from the reaction environment. And then barium 2 plus aqueous plus 2 nitrates. Okay, so which term is there? 2 barium 2 pluses? Nope, it's only 1. Chlorides says B is 1. We have 2 actually. 2 silvers. There it is right there. 2 silvers. So that's C. And then 40 simply gets rid of, we're looking at net ionic equation. We get rid of the spectators. Barium's gone, nitrate's gone. Now we have is 2 chlorines, 2 silvers, and 2 silver chloride, but that's not the simplest form of the equation. We have to reduce it by 1. So 1 silver plus 1 chlorine yields 1 silver chloride. That's the trick for this one. Don't forget to, when you can, reduce a balanced equation and the coefficients to a lesser number, as long as the ratio stays the same. If we've got 2, 2, and 2, then the simplest equation is 1, 1, and 1. So that's why the answer is A. I don't know why they didn't put a 2 Ag plus in there. That would have been a trap. Okay. Let's see, 45. When solutions of strontium chloride and sodium sulfate react, which of the following is a spectator ion? Okay, strontium chloride. Strontium is in the second column, so it's a 2 plus. That means we need 2 chlorines. That's aqueous. And it's reacted with sodium sulfate. Sodium sulfate is a polyatomic with a 2 minus, so we need 2 sodiums. Aqueous. And those are aqueous solutions. So who gets together with whom? If we're looking for the spectators, we want the ones that don't react. The solid that's formed is strontium sulfate. So that leaves chloride and sodium ions as spectators. So our choices are chloride ions, sodium ions, 2 of the above. Okay, that's why E is the answer. Because we have both this one and that one as spectators. Hmm. 50. What mass of sodium hydroxide is required to react exactly with 25 milliliters of sulfuric acid? All right, so we have acid-base reaction. I'm not going to put the phases in there. Sodium hydroxide yields sodium sulfate plus water. So the balance would be 2 of these and 2 of these. Okay, now what we're given is 25 milliliters of 2.7 molar sulfuric acid. 25. Oh, only 1 0. Milliliters of 2.7 molar. Okay. And the question is, what mass of sodium hydroxide? So we need to find out how many moles of sodium hydroxide are required. And molarity times volume equals moles. So if we say, let's convert this to liters, that would be 0.0250 liters. Yeah, 0.025 liters. And 2.7 times, which would be 6.75 times 10 to the minus 2 moles of H2SO4. We convert that, get rid of the sulfuric acid and leave us with sodium hydroxide. Ratio is 2 to 1. But 2 times that would give us 0.135 moles of sodium hydroxide. Now we can convert that to mass. Moles, mass. Sodium is 23, oxygen is 16, and hydrogen is 1.01. So that's 4001. Times that number I've already got in my calculator. 5.4. 5.4 grams. Okay. Let's see. Never ending. Actually, I really did need 2 days for this one. I need to remember that next time I put a syllabus together for this thing. 52. In which of the following does nitrogen have an oxidation state of +4? All right, A, B, C, D, and E. Separate them out. HNO3, NO2, N2O, NH4Cl, and NaNO2. And we're looking for the oxidation state of nitrogen. Each one of these. Nitrogen, and nitrogen. Okay. Let's see. This is +1. This is -2, so that's -6. And a +1 is -5, so this one has to be a +5. That's not it. This one's -2, that's -4, this is +4, that's it. B. We can do the rest of them. -2 here, so this one has to be a +1 each. And this is -1, +1, so that's +4, -1 is +3. That's a -3. And then this is -2 and +1. -2 is -4, and +1 is -3, so this is +3. Okay. So we've got a whole range of oxidation states for nitrogen. And if you look in that little box on your periodic table, you'll see, a list of lots of numbers. #53. Oxidation state of iodine in IO3-. Okay, -2 here times that is -6, but we only have to balance 5 of those because we want to hold one out for that. So iodine is +5. Which of these statements is not true? Or 55. When a metal reacts with a nonmetal, an ionic compound is formed. That's true. B. A metal nonmetal reaction can always be assumed to be oxidation reduction reaction. If it's elemental metal and elemental nonmetal, yes, that's true. 2 nonmetals can undergo an oxidation reduction reaction. Oh yeah, happens all the time. They just change oxidation states. That's all it's required. When 2 nonmetals react, the compound formed is ionic. Nope. And the last one should be true. A metal-nonmetal reaction involves electron transfer. Yep. That's the same as B. So D is the bad one. Okay. Oh, 56. In the reaction, 2 calciums and 1 oxygen yields 2 calcium oxide. Which species is oxidized? All right. Plus 1 oxygen yields 2 calcium oxide. All right. We're looking for the one that oxidized loses electrons. Oil, oxidation is loss. So these are zeros. This one is a 2+ and that one's a 2-. So the one that loses calcium, that's the one that's oxidized. The calcium element, not calcium 2+, but calcium. Right? To go from here to here, we have a loss of 2 electrons per calcium. That would make it the reducing agent because it's oxidized. Okay, 57. What's going on here? In this reaction, cesium plus chloride yields cesium chloride. Chlorine is Reducing agent, oxidizing agent, okay. 2 cesiums plus 1 chlorine, right? And 2 cesium chloride, 2 cesium chloride. All right, so if we go from this one to this one, we went cesium. Yeah, that makes sense. This is a +1, that's a 0. This is a 0, this is a -1. So this one is oxidized. This one is reduced. And the reducing agent, we say in effect chlorine. This one is not the reducing agent because it was reduced. It's the oxidizing agent. It's the oxidizing agent. And the others, chlorine is not oxidized, it's reduced. And it's not the electron donor, it's the electron acceptor. All right, so only B is correct for that series of possible answers. Uh, 61. Which of the following statements is or are true? Oxidation and reduction, A, cannot occur independently of each other. A is true. Always occur together. B, accompany all chemical changes. False. C, describe the loss and gain of electrons respectively. Oxidation is loss, reduction is gain. Oil rig. Yes, C is also true. D, result in a change in the oxidation states of the species involved. Well, yeah, that's definition. So that means E is A, C, and D. Right, that's true. '63. Balance the following oxidation reduction reaction using the oxidation number method. Okay, so we're going to start off with iron, react it with bromine. That ought to be a fun reaction. And we get Fe3 plus and Br minus. Okay, so this is 0, this is 0. And if we go from here to here, that's a loss of 3 electrons per iron. And this one is a gain of 1 electron per bromine atom. How do we get them to balance? Well, we can't make 3 out of that because 1 times that is 2, and 2 times that is 4, right? So we're stuck. What we have to do is cross multiply, actually. So if we say 2 times this one times 2 is equal to 6 electrons. Now we can say 3 times this one and 6 times that one. Right? 6 bromines times 6 equals 6 electrons. So it should be 2, 3, 2, 6. In the balance equation, the coefficient for bromide is 6. Our objective here is simply to make the same number of electrons lost as gained. Any way you can get there. All right. Uh, 66. Select the spectator ions for the following reaction. All right, here, what we need to do is say, all right, which one's the solid? Lead 2 chloride, right? Lead 2 chloride. Lead and silver chlorides are always insoluble. So the spectators then would be potassium and nitrate. And A looks like the best answer. 68. Scroll a little bit and pick up 9 also. Identify the precipitate formed if any of the following reaction in aqueous solutions. Okay. Identify the precipitate. All right. Anything with nitrate is going to be soluble. So, and anything with ammonia, so double whammy. Ammonia and nitrate are soluble. So the other option is iron 2+ and carbonate. We looked that up in our table, and we find that this is insoluble. And since this is a 2- and that's a 1+, 1 iron and 1 carbonate is all you need. That's why B is the answer. 69. In which of the following does nitrogen have the highest oxidation state? We looked at this one earlier, didn't we? I should have left that up there. Let's see how quick we can get this done. B, C, D, E. All right, HNO3. -2, -6, +1 is +5. That's a -5. That's probably not going to be a candidate. Oh, excuse me. Yes, it is. Went the wrong way. -6 and +1 is -5 and +5 for nitrogen. That's probably the right answer. I don't think it goes any higher than +5. We could do the others. NO2, so that'd be a +4. And N2O would be a +1. And ammonia, that would be -3. And the last one, NaNO2, is +3. I think. Yeah. So A is our best answer. +5 is the highest oxidation state. '71. In which one of these does iodine have the lowest oxidation state? It could be the lowest positive number, or it could be a negative number. Okay, got that one 0. NH4I. This is a +1, so this one has to be a -1. I2O, that's a -2, so this one has to be a +1 each. There. B is IO2. This would be a -4, so this has to be a +4. And LiIO3. That's a +1, -6, -5, +5. So the lowest number is going to be D, -1. I think we're done. These other balancing equations, I might have put one of these types in as a bonus. This one's going to be fairly straightforward, right? This is nitroglycerin. What happens to nitroglycerin when it gets bumped? It goes up in 4 different gases. This one is a difficult one right here. Why don't we do this one? I mean, we're already here forever. Might as well do this one. this is the type of reaction that you need to balance the electrons first, and then use that as your starting point for the budget method. So Ki, let's see, I need some more room. 78, was it? So we got Ki, and then we've got HNO3. And that yields KNO3 plus NO plus I plus H2O. All right. So let's find out what happens to what. This is a +1. This is a -1. That's a +1. This is a -2. So -6 and +1 is -5. This has to be a +5. This is going to be a +5 also, because it's a nitrate, both sides. So that one, it is not a participant in the oxidation reduction. This one is -2 +2. And this one is. This is -2 and +1. Okay, so what happened to what? Potassium didn't change. Iodine did change. It had to lose an electron. Loss. 1 electron per iodine. Okay? Nitrogen. It didn't change to there, but it did change to here. Okay? So this is a gain. 3 electrons per nitrogen. Right? 3 negatives plus a +5 yields a +2. So that's our starting point. We want to balance the number of electrons transferred. All right. Can we get 3 electrons? Well, actually, this has already got 2. So if we put a 2 here, times 2 equals 2 electrons. All right. So now we've got this part balanced, but we're at odds with this one. So we need to bump this one up by 3 and bump this one up by 2. Okay. So if we bump this one up by 2, that's 2 ends and 2 ends. We're ignoring this one for now. Then that's times 2 would equal to 6 electrons. This one would be times 3. So times 3 from what's already here is 6 and 6. So far, so good. Now, let me see if I messed up. I think I did mess up. See, we started off with AI. We need I2. That's fine. Oh. That's where I went wrong. Wait a minute. I knew it didn't look right. Six iodines. 2 times 3 is 6. Okay, that one's good now. This one should be just like that. Right, 2 times, we did 3 minus. Okay, now we're good. Okay, now we can balance it by the budget method. So we balanced our electrons. Now Let's clean it up a little bit. Let's see. That's 3 there. Let's change this to 6. Okay, now we can do the budget. We might not even need to. We might be able to do it without throwing the budget into it. No, we better. Okay, potassium, iodine, hydrogen, nitrogen, and oxygen. So we got 6 potassiums, 6 iodines, 2 hydrogens, 2 nitrogens, 6 oxygens. We got 1 potassium, 6 iodines, hydrogens, 2, and nitrogens. We got 1, 3, and oxygens. We got 3, 4, 5, 6. Okay. So if we balance the potassiums with a 6, right? That's going to give us 6, 7, 8 nitrogens. Okay. And 3 times 6 is 18, 19, 20, 21 oxygens. Okay. Nitrogens on this side, we need 8 of them. Right? Okay, that's going to give us 8 hydrogens, 8 nitrogens, 24 oxygens. Okay. Now we got to balance hydrogens and oxygens. So hydrogens over here, we need 4 of these, correct? That gives us 8. That's 4 oxygens plus, let's see, 4 plus 2 is 6, plus 18 is 24. There we go. So at 4, 3, 2, 6, 8, and 6, we're balanced. That's a lot of work. There's a sense of satisfaction when you solve one of these bad boys. Are we? Yeah, we're done. Because that was not marked and I just wanted to do it for the fun.